In this video, we're going to talk about the ideal gas law, guys. This might be the most important gas law to remember, because if you remember the ideal gas law, you can derive all the other ones. Okay, what are the other ones we learned? We learned Boyle's law, Charles' law,
I don't see you, bro.
Avogadro's law. You can get all of those from this one single gas law called the ideal gas law. So if you're watching along in the video, please have your guided notes out, filling them out as we go through these slides. Here we go. Okay, the ideal gas law combines Boyle's. Oh, we forgot Charles. We did Charles' law too, right?
Yeah.
So Boyle's law, Charles' law, Avogadro's law into one equation. It combines all of them and makes it nice and easy to remember. The ideal gas law equation, maybe one of the most famous equations in chemistry, is right here. PV equals nRT. PV equals nRT. If you remember that, I will show you, you can derive Boyle's law, Charles' law, Avogadro's law, just from this single equation. So it's by far the most important one to remember this chapter. PV equals nRT. Okay, when you look at the ideal gas law, the P stands for what, guys?
Pressure.
Pressure. Has to be in atmospheres. Volume is the V. What does it got to be in? What units? Liters. What's the N, guys? Moles. R is a new one, okay? We're going to talk about what R is. It's the gas constant. We'll talk about it here in a second. And what is T? Temperature, and it has to be in Kelvin. So pay attention to these units here. Okay, we've got to make sure that when we do the ideal gas law, we're in these units. Okay, so there's that new variable, R. We haven't talked about it yet in this chapter. R is the universal gas constant. Universal gas constant. And it's a constant, so it equals something. R is equal to 0.08206. 0.08206. And I want you to pay attention to the units of R. Okay? The units of R, it's measured in liters, atmospheres, divided by Kelvin, moles. So we've got to make sure that when we do the ideal gas law equation, we're in liters, we're in atmospheres, we're in kelvins, and we have moles. Okay? If you get to those units, then everything will be pretty easy after that. Okay, let's do a practice problem with this. Let's get right to it. A sample of hydrogen gas has a volume of 8.56 liters. I always like to underline what they give us. Okay? So it's given us a volume there. A temperature at 0 degrees Celsius and a pressure of 1.5 atmospheres. It says calculate the moles of hydrogen. So we need moles. Circle what they want us to find. Present in this gas sample. Okay, now we're learning about the ideal gas law. What was the equation, guys?
PV equals nRT.
PV equals nRT. Now let's plug in. What was pressure? 1.5 atmospheres. Yeah, it said it right here. So pressure of 1.5 ATMs. Okay. Now we need V. What was volume? 8.56 liters. Yeah, it's right here. So 8.56 liters is equal to
5.
And did it tell us moles, guys?
No.
It didn't tell us moles, did it? That's what we got to find. So I'm going to keep it as N.
Can you wait till I'm looking?
Okay. So we don't have number of moles, so I'm going to keep it as N. What about R? What is R again? The universal gas constant. and it's equal to 0.0, what is it, guys? 8206. Okay. And T stands for temperature, but what does that temperature got to be in? Celsius or Fahrenheit or Kelvin? Kelvin. Okay. It said the temperature was at 0 degrees Celsius. How do we get to Kelvin again, guys? Yeah, we're going to add 273 to our degrees Celsius, so that comes out to be 273 Kelvin. Okay. All right, now we have an equation with one unknown. Can we solve for n, the number of moles? Sure. What should we do to get n by itself, guys? Let's divide both. Let's divide it by 0.08206, and let's divide it by 273 Kelvin. But if I do it to one side, do I have to do it to the other side?
Yes.
Yeah, so 0.08206, and we're dividing it by 273 Kelvin again. Okay. What happens over here, guys? They cancel. Yeah, they cancel out. Anything divided by itself is 1. So n, number of moles, equals 1.5 times 8.56 divided by 0.08206 divided by 273. Take a second, get a calculator. Let's see what you guys get. Okay, I'm finding that n is equal to 0.57. And what are the units for n? Moles. Moles of what? What are we talking about? Moles of H2, right? Hydrogen. Moles of H2. Okay, so I'm going to put that and circle it. Okay, let's see if we did it right. The answer was 0.57 moles of H2. Yes. So that's the ideal gas law. Some of the things that you could get in trouble with is make sure that you've got the units ATMs, liters, and kelvins. If you're not in those units, you'll have to convert to get to those units. But we know how to do that. Okay.
Why are you so mean?
All right, now we're going to get into problems that are a little bit trickier. Please be paying attention as we go through this next part, and it will make it so easy, okay? Use the ideal gas law to solve problems. In dealing with changes in gases, we always place the variables that change on one side of the equal sign and put the constants on the other side. So variables that change is going to be on one side of the equal sign, and we're going to put the ones that don't change, the constants, on the other side of the equal sign. Let's see how this works with several examples. I've got a lot of practice problems coming up. Please watch how I do it, because if you don't, it will be a little complicated. Here we go. Practice problem number 8. Let's read it, and then we'll decide what it's asking us. Suppose we have a sample of ammonia gas with a volume of 7 milliliters. Okay, so it's given us a volume, I underline it, and a pressure of 1.68 atmospheres. So it's given us a pressure. The gas is compressed to a new volume of 2.7 milliliters at constant temperature. Use the ideal gas law to calculate the final pressure. A couple of things that I would probably change before we start doing anything. And that's the units here. It's in milliliters. How do we get that to liters? 3 to the left. So 1, 2, 3. So what does that become? 007. I like it.
My favorite.
Okay. Let's do it to this final volume. What's this final volume going to be? Isn't it going to be 0.0027 liters? Okay. And the pressure was in atmosphere, so that's what we want, so I'm not going to change that. Okay, now it says use the ideal gas law to calculate the final pressure. What I want to see you guys write down is the ideal gas law every time. PV equals nRT. Here's what I do. You can do it different if you want, but here's what I do. I put a little dot above the variable that changes. Is pressure changing here?
No.
Yeah, we're going to calculate the final pressure is what we want to find out, right? So pressure is changing. So I'm going to put a little dot there because that variable is changing. Is volume changing?
No.
Yeah, it is. Yeah, we're changing the volume. So put a little dot there. Okay. Now, is number of moles changing? Did it tell us that it was changing? No. So I'm not putting a dot over it. What about R? Does it ever change? No. It's always a constant. Is temperature changing? No. Okay.
Free damage.
Now watch what I do here. If you have two variables that are changing and they're equal to a constant, well, what they change into, we're going to call this one P1 and V1, and they're already on the left side. So let's keep it there. So I'm going to call that initial. But they're equal to these constants right here, nRT. Well, pressure and volume are changing, so I'm going to call it P2, V2. Okay? They're changing to something new. Well, look at this. Let's look at the math here. If this term right here equals the constants, and the constants equal this term right here, what can you say about these two things? So I guess what I'm saying, let me explain it a simple way. If A equals B and B equals C, how does A and C relate? They've got to be equal. Okay? Yeah, they would be equal as well. So can I set this up like we did before with Boyle's law? P1 V1 is equal to P2 V2? Guys, we just derived Boyle's law, right? I mean, that's how they get Boyle's law. Okay, so we just derived Boyle's law. Now let's plug in to our variables and solve this problem. Okay? What is P1? What was pressure initially, guys?
0.007.
Wasn't it 1.68 atmospheres?
Yeah.
1.68. What was volume initially? 007, right? And that's equal. We don't know the final pressure. That's what we're trying to find out. What was volume final? Okay. That should be a 0 here. Something's happening. Okay. How do you solve for P2, guys? Quickly. Divide by 0.0027. Both sides? Okay. Over here it cancels out, which is what we wanted. So P2 equals, try it on your calculator, 1.68 times 0.007, and then divide that by 0.0027. Okay, so I'm getting that P2, final pressure, is equal to 4.36. What's my units going to be for pressure, guys? Atmospheres, ATMs. Okay, let's see and kind of make sure this makes sense to us. If volume decreased, so volume went down, what would happen to the pressure?
It go down too.
It should go down as down.
Up.
If volume decreases, pressure should go up, right? And that's exactly what happened. Volume and pressure are inversely related. Okay, and that's what happened, so it does make sense. Let's see if we got it right. 4.4, yeah. If you round, if this 6 would round that 3 up to 4, so 4.4 atmospheres. Very good. Okay, let's do another one like this. A sample of methane gas that has the volume of 3.8 liters at 5 degrees Celsius is heated to 86 degrees Celsius at constant pressure. Calculate its new volume. Okay, I would like to underline what it gives us. Volume of 3.8 liters, nothing wrong there. Its temperature was at 5 degrees Celsius. Let's change that to Kelvin right now. What is that? So Kelvin is equal to 273 plus your degrees Celsius. So what's 273 plus 5? 278 Kelvin. Okay. And it's heated to 86 degrees Celsius. What is this going to be now? What's 273 plus 86? Can somebody do that for me?
359.
359?
Yes.
Kelvin. Thank you. And it's at constant pressure. Calculate its new volume. So that's what we're looking for, is the new volume. So circle that. Okay. With all gas law problems, you can write the ideal gas law equation down. I'd like you to do that right now. So PV equals nRT. Now, put a dot above the variables that are changing. Is pressure changing?
Yep.
It said constant pressure. So is it changing?
No.
No, I'm not going to put a dot above pressure. What about volume?
Yes.
Yeah, we're going to get a new volume instead. So that's going to change. Is number of moles changing?
No.
No. Is R changing?
No.
No, it never changes. Constant. Is temperature?
Yes.
Yes. So put a dot above it. Okay. Now, we learned that we want to put all the variables that change on one side and keep all the constants on the other side. I like to move the ones that are changing, the ones with dots, to the left side. How would I get T on the left side?
I don't know.
Yeah, let's divide by T with the dot. Okay, divide by T with the dot. Okay, over here, don't they cancel out?
Yes.
Sure. Now, I've got pressure that's not changing. I want it on the other side of the equal sign. How do I get it on the other side? So we're timesing here, so what do I have to do to take it out? Divide by P. Both sides divide by P. Over here, it cancels out. And so it's getting a little messy. Let me rewrite this to what I've got now. Don't we have V with the dot divided by T with the dot is equal to NR divided by P?
Yes.
Okay. Okay, now that's important to do. If you can do that every time, this will be no problem. Okay? Okay, so once you get all the variables that change on the left side and all the constants on the right side, now let's go through this one more time. These are changing, so I'm going to put a little 1 right here. Well, they're going to be equal to these constants, but what they change to is also going to be equal to the constants. So V1 or V2, because it's going to be final, over T2 is also going to be equal to those constants right here. Okay, again, if A equals B and B equals C, how are these two related? They equal each other. So let's rewrite that. V1 over T1 is equal to V2 over T2. Guys, what gas law is this? That's Charles' law.
Yeah.
We just showed you how to derive Charles' law. So you don't ever have to remember it anymore, as long as you can remember the ideal gas law and do this reorganization of variables here, you can always remember Charles' law. Okay, now let's plug in, okay? What's V1? What's volume initially?
3.8.
Okay, 3.8. Okay. What's T1?
278.
Yeah, that was the 278 Kelvin right there. So 278. And that's equal to, what's V2? Yeah, we don't know the new volume. We're trying to find it. So I'm going to call it V2. And what's temperature final?
359.
Yeah, 359 Kelvin. Okay, what would you guys do to get V2 by itself? You would divide? Yeah, multiply. Let's times 359 both sides. Okay? 359 both sides. Over here, why do we times? Well, because now it cancels out. So V2, let's calculate it real fast. 359 times 3.8. And then divide that by 278. Are you guys getting that the final volume is 4.91 liters?
Yeah.
Okay, let's see if we're right. 4.9, yes. So let's see if that makes sense here, guys. Temperature, what happened? We got a lot higher temperature. So as temperature goes up, what happens to volume?
It goes up.
It goes up. Did the volume go up?
Yes, indeed.
Now we started at 3.8 liters and we ended at 4.9 liters. So we should always, after you get an answer, make sure that it makes sense intuitively. Okay, number 10. I want you guys to try this one.
Okay.
There's going to be some unit conversions. I want you to try it. If you're watching the video, hit pause. Try it before you continue on. That's how you learn. Okay, let's go through this problem. This is a great problem. This is about as hard as it will get. So what I would do is read through it. Let's read through it. A sample of diboron gas, B2H6, a substance that bursts into flame when exposed to air, has the pressure, I always like to underline what they give us, of 345 torr. Now that's a problem. What do we want our pressure in, guys? Atmospheres. So let's change that right now. 345 torr. If you remember the conversion factor, and I will always give them to you on the test, but if you remember the conversion factor, if torr is on top, where does torr got to go? On bottom. There's 760 torr in how many atmospheres? In 1 ATM, right guys? Okay. So if you do that on your calculator, the torr here is going to cancel out and we'll be left with ATM. Are you guys getting 0.45 ATMs? Okay. So that was our initial pressure. And it says at a temperature of minus 15 degrees Celsius. Can we keep it in Celsius? No, let's change it to Kelvin. So 273 plus a negative 15. What is that? Are you guys getting 258 Kelvin?
Yes.
Right? Yeah. And a volume of 3.48 liters. Well, good. We don't have to convert that one. And it says, if the conditions are changed so that the temperature is then 36 degrees Celsius, let's convert that to Kelvin. What's 36 plus 273?
309.
309. 309 Kelvin. Good. And the pressure is 468 torr. Again, we're going to have to convert this. So 468 torr, put it over 1. If torr is on top, where does torr go? Bottom. There's 760 torr in 1 atmosphere of pressure. So what do you guys get when you do that? Yeah, 0.62 atmospheres, okay? So this goes to 0.62 atmospheres. Okay, and then it says, what will be the new volume? So we're going to solve for volume here. Okay, there's a lot going on. What's your first step once you get everything converted and you read through it? You write down what gas law? The ideal gas law. So let's write that down. What is it, guys?
PV equal nRT.
Good. Okay, now let's put a dot above the ones that are changing. Is pressure changing here?
Yes.
Yeah, pressure's changing. So put a dot above it. Is volume changing? Yeah, we're going to get a new volume. That's actually what we need to find. Is the number of moles changing?
No.
Nope, didn't say anything. R never changes. It's a constant. Is temperature changing?
Yes.
Yeah, so now we have 3 variables that are changing. Now remember, everything that changes we want to have on the left side. Everything that stays constant we want on the right side. So how would I get this T dot, because it's changing, on the left side? Divide by T dot, right? Both sides. Over here, it cancels out. So let me rewrite that so that it's a little cleaner. So P dot V dot over T dot is equal to the things that don't change. The constants here are moles and the universal gas constant. Okay. Now guys, if pressure and volume and temperature are changing, but they're equal to these constants, whatever they change to is going to be equal to these constants as well, because it's not changing. So whatever they change to is also equal to the constants. So P2, V2 over T2. And I call everything with a dot 1. Okay? So again, if A equals B and B equals C, how do these two things relate? They're equal to each other. So let's write that formula. So P1, V1 over T1 is equal to P2, V2 over T2. Okay. Are we good with that part, guys?
Yeah.
I hope so. Now let's plug in what these variables were. What was pressure initially? Wasn't it the 0.45 ATMs? Okay, so 0.45 ATMs. What was volume initially? 3.48 liters. Okay. What was temperature initially? Yeah, it was this minus 15 degrees Celsius, 258 Kelvin. Yeah, thank you. 258 Kelvin. Okay, that's going to be equal. What was pressure final?
0.62.
Good. So 0.62 atmospheres. What was volume final? We don't know that one, so I'm just going to call it V2. And divide it by, what was temperature final? Let's see, where was that? Oh, okay. Yeah, 309 Kelvin. Yes, thank you. 309. All right. Now, there's a lot of different ways you can solve for V2. What I would do is try to get this 309 off the bottom. How would you guys do that? Let's times both sides by 309. Okay? Times both sides by 309. It's getting a little messy here, but we'll get through it. Okay, that cancels it out on that side. Now what do you got to do? Yeah, to get V2 by itself, we've got to get rid of this 0.62. Let's divide it by 0.62, both sides. Okay, over here, the 0.62 cancels out. And so we're left with this big, huge term here is equal to V2. Let's put it in a calculator and see what you guys got. So 309 times 0.45 times 3.48. And then take that answer and divide it by 258. And then divide that answer by 0.62. Okay, I'm getting that the final volume, V2, is equal to 3.03, if you round it. And what's volume, what are the units? Liters. Did anyone else get that?
Yes, I did.
Okay, good. Let's see if we got it right. So 3.07. Yeah, we just rounded a little bit, so that's close. Close enough. Okay, so good job. Okay, practice problem 11. This is the last practice problem using the ideal gas law. So I want you guys to read it, try it on your own. If you're watching the video, hit pause, try it first on your own, and then hit play and see if you got it right. That's how you're going to learn this stuff. Okay, let's see if you got it right. a sample containing 0.35 moles of argon gas, I'll underline that, it gives us moles, at a temperature of 13 degrees Celsius. Guys, 13 plus 273, help me out, what is that? 286 Kelvin. Always got to convert to Kelvin. And a pressure of 568 torr. Wow, that's, we just got to convert this to what, guys? To ATMs. So 568 torr, put it over 1. If torr is on top, what goes on bottom? Torr. There's 760 torr for 1 atmosphere. So when you do that, what do you get here, guys? 0.774? Okay. And that will be atmospheres, right? Okay, good. We got that in atmospheres now. It's heated, so we're changing the temperature here to 56 degrees Celsius. What's 56 plus 273? 3 what?
329.
329 Kelvin. Yeah, thank you. Okay, so 329 Kelvin. And then the pressure ends up being 897 torr. Let's convert that one again. 897 torr. Put it over 1. Torr is on top, it's got to go on bottom. There's 760 torr for 1 atmosphere of pressure. Again, I'll always give you the conversion factors here on the test or a quiz. Okay, so when torrs cancel out, 897 divided by 760, 1.18 atmospheres. Good job. Okay. Then it says calculate the change in volume. So volume is what we really want to know, the final volume. Okay, we get to this part. Everything's converted. We got all the units right. Now what do? What gas law do I write down? Ideal gas law. So what is it?
PV or NRT.
Good. Now what do, guys?
Figure out what's changing.
We need to, figure out what's changing and put a what above it? A dot above it. Is pressure changing?
Yes.
Yeah, we calculated a couple of pressures up there, so we know what's changing. Is volume?
Yes.
Volume changing? Calculate the change in volume that occurs. Okay, so volume is changing, right? Okay. Is number of moles changing? No, it told us moles, but it's not changing. So we're going to keep that one without a dot. Is R changing? No. And is temperature changing?
Yes.
Yes, so put a dot there. Okay, so we've got the variables that are changing with a dot above it. But we have one problem here, guys. What is it? We don't know initial volume, do we? So how can we find initial volume? We have pressure, we have moles, we have R, and we have temperature. Couldn't we use the ideal gas law to solve for the initial volume? Okay, let's do that. I'm going to do it up here. So PV equals nRT. Now let's plug in. What's pressure initially? What was it, guys? 0.74 atmospheres?
Yes.
Okay. We don't know volume initially. I'm going to call it V1. Is equal, what was the number of moles? 0.35. What's R again, guys? Okay. I'll always give you that, but we're going to use it so much you're probably going to memorize it anyway. And what was temperature initially? 286 Kelvin. Okay. Now, I would divide both sides by 0.74. Over here, it cancels out. Let's see what the initial volume was. I'm getting that V1. Are you guys getting this? Was 11.1.
Yep.
And what units is that going to be in? Liters. Okay, that's not my answer. That's what volume was initially. Okay. So we would have eventually had to solve for that. But now, let's go back to the ideal gas law. What do we need to do if they're changing, guys? These ones with the dot. What do we need to do?
Move it to the same side.
Move it to the same side. So let's move T dot over to the left side. How would I do that?
Divide by T.
Divide by T dot, right? Okay. Over here it cancels out. So I'm getting this PV over T is equal to NR. Yeah, pressure, volume, and temperature are changing, but they're still going to equal these constants, right?
Right.
And whatever they change to, isn't whatever they're changing to going to equal the constants as well? So P V over T, I'm going to put 2 here because that's what they're changing to. And put 1 here because that's what they are initially. And so we can say that they're going to be equal to each other, right?
Yes.
So P1 V1 over T1 is equal to P2 V2 over T2. Now let's just plug in and solve for the final volume. Okay, what's pressure 1? Help me out, guys. I'm going to come over here.
0.774.
0.74 atmospheres, good. What was volume initially? Yeah, we solved for it up here. Initial volume was 11.1 liters. Let's divide it by temperature. Initial is what? 286 Kelvin. Okay, all of that is going to be equal. What's pressure final? Yeah, that's what we solved for here, 1.18. Okay, now we need volume final. Do we know it? Nope, so I'm going to keep it as V2 and divide it by temperature final. What did the temperature get to? 329 Kelvin. Okay. All right, so there's our equation with one unknown. What I would do is times both sides by 329. Okay, over here it cancels out, which is what we wanted. And divide each side by 1.18. Okay, over here it will cancel out. So V2 equals all of this stuff right here. Let's try it. 329 times 0.74 times 11.1. That answer, and then divide it by 1.18. And then divide that answer by 286. Are you guys finding that V2 is equal to 8.0 liters? Did anyone else verify that? Okay. Final volume of 8 liters. So what happened to our volume, guys? It went down. It went down. Okay, let's see if we can make sense of that, because temperature went up. Temperature went up. What should volume do if temperature goes up? It should go up, but there was another variable changing. What was it? Pressure. Pressure was initially 0.74, and finally the pressure went up. So the pressure went up, which should make volume go down. And so, does that make sense? What happened there? Our volume did go down, didn't it? Yeah, it went from 11.1 to 8. And so, yeah, that's one of those ones where you're just going to have to use the equation to figure out what's happening. So, okay, good job. Let's see if we did it right. The answer is a minus 3 liters. Oh, it wanted to change in volume. So if we were initially at 11 and our final volume was at 8, what's the change?
-3.
Yeah. So if we were at 11.1 and we ended up being at 8 liters, we lost 3 liters, right? So the change, yeah, if we really answer this question, is a minus 3 liters. We did the problem right, we just didn't read it carefully at the end. Okay, good job.
That's a problem.
That's a good problem, isn't it? Yeah, if you can do that one, yeah, you can do any of these, so good job. Okay, I've got a summary of the gas laws that we'll finish up on. Okay, so in your guided notes, there's a summary of the gas laws table. Take a second to fill this out on your table. Okay, so this is a good table that summarizes all the gas laws that we've talked about in this chapter. We talked about Boyle's law, Charles' law, Avogadro's, and then most importantly, guys, if you remember the ideal gas law, PV equals nRT, you can derive any of these other ones. Just remember, put a dot above the ones that change, move it over to the left. Everything that doesn't change, move it to the right, and set them equal to each other. And you can solve all these problems. Hopefully that helps. There is a worksheet in your student workbook. It's titled Ideal Gas Law Worksheet. You should know how to do all of it now, so hopefully this helps.